Thank you for your attention. If you have any question, please feel free to ask.
Thank you, Yegor. Colleagues, any questions? No. So I have one. Which cyber threats maybe are identified as the most critical for swarm operations? And why?
Most critical, it's GPS spoofing and jamming attacks, because it's most popular technique and maybe most usability technique, because swarm drones can't I don't know how it will be in English, like орієнтуватися in area which they are working, and
Thank you for your answer.
I can continue. I'm so sorry.
Yeah, sure, please.
Yes, and when for example, GPS data is compromised, it's can to follow us in failure situation when swarm drones contact another aim, for example.
Okay, thank you, dear colleagues. Any questions? No? So thank you for your report. Let's move on. So is Bogdan Semenyuk here?
Yeah, here.
Yeah, are you ready? Please share your screen.
Moment, yeah.
And you may make your report up to 12 minutes, please.
I believe it's on the screen now.
Please switch to a presentation mode, please.
Yeah, sure.
Yeah, it's okay. Please start. You may start.
Moment, it's switching to different display. Or you see it correctly?
Everything is okay. You may start.
Okay, thank you. Just a moment, I need the notes. Yeah. So, good afternoon everyone. My name is Bogdan, and I'm here to present work on signature preventing balancing method for intrusion detection and well-known approach for IDS system. So it's new look how we can balance the learning data set to have it more properly set it for our neural network. Yeah, and also it a bit with rely on the previous work with sonification, but I will show it in the next screenshot. So first one is motivation. So about that the modern networks, especially Internet of Things, generate huge and complex traffic flows. So intrusions detection systems work on that very well, but a bit one area is still open to discuss. This area about less present attack types, so that system could not work with them good as with all well-known attack types. So idea is still to correctly balance and provide more missing types to increase accuracy. Next one is about current researches. So goal is to improve detection rates on rare attacks while keeping overall current accuracy high. We introduce an adaptive sampling method which process attack signature instead of distorting them. And nowadays is two methods where we can dive deeply into. Is about that, as we already know, I shared that improving dataset balance, and the second one is feature selecting. So here we dive into the first one, and let's move on. Rated work, existing IDFs is yeah, sorry, same slide is already shared my knowledge about the selection, feature, and balancing, but here additionally I could add that also generative networks could help us, and yeah, focus on rare attacks for hours. Smarter NC's improved version of Smarter, what is present here. Next one is the dataset. So to start with that problem, we should firstly look into the dataset and take a look on that, how data is present and how it is grouped. And here also, as I mentioned, is applied to existing my approach with that converting to each attack to sound, and was tested on that one pipeline also. The dataset itself is present for us 41 feature and 4 tag groups with strong imbalance of classes, because it could be around a difference between 4,000 of present tag types and even to 400. So it's a big difference between, and for example, CNN could not learn on that rare types correctly. Example is a user to remote is not very populated in this data set. Yeah. Next one is a couple words about that scenification process. So this is pipeline with limited around 0.4 seconds for each sound, and 2000 hertz for that sound was used because of complexity of calculation on system. And yeah, let's move. The most interesting part is about method itself. So here's the picture how it basically, when you work with it, how it's done. So you should increase the amount of rare attack types by creating a new version of that based on existing signature. So existing method like Smarter uses that random coefficient for that, so it could corrupt our like anomalian signature of certain methods, so it will create not a good example of that. So, and on the test run, it will give not good result. Also, random coefficient for creating a new records of rare types will provide us different results when you run it multiple times in one row. So it could be difference around 10% for that. And in proposed method, we use median, where is the percentile around 10 to 19. So we keep imbalance. It was proposed from dataset originally as it expected. So we're not going lower on higher than average value of each attribute of that. So we have 41 attribute for that one. And for creating a new one, synthetically, we rely on not a random coefficient, or on deterministic coefficient for that one. And main idea is when you populate the data, you should have that original signal where you see that anomaly is present, and you correctly keep those original signature or certain method, like you have DOS or DDoS attacks. The next one is experimental setup. So comparing these two proposed new method, SPS and SMOTE, was compared with on that dataset KDD, and also was used at well-known metrics for that, accuracy recall and macro recall. And what we have as result, it is base accuracy was without any additions was around 76% and recall 72%. So with base model, and also the next apply was well-known approach, and gives us with a random coefficient around 79 accuracy and recall 70. And the next one is proposed method with deterministic coefficient, and saving that original signature give accuracy around 81% and recall 73%. So from original, improvement is 11%. And the next one is per type improvement of recall. So there's a group of rare attack types like guest password, 48% of recognition, which give us pictures that we work in correct way, that it could be improved. So that number deeply relates on setup, like you configure that method. So it means how much you created those records from original amount. So if, for example, we have 400 examples, so we should create the median, how much we have for each attack type, and we aim is to reach those medians. So for example, for those datasets is around 2,000 records for each one was reached. And here we also could see other attack types was improved. And here is more deeply picture of that we could see on that chart, that each attack type how was improved that recognition by system. Yeah. Here is the top 20. And next time. So yeah, time was also checked, because we also need to be sure about total training time is a decrease or increase. And here we have a bit decreasing time. So I was a bit surprised with that, but I believe something was changing on that Google co-op site. So I will create a new couple runs to measure how it works with same hardware. And maybe I will use my own hardware. So I think, yeah, conclusions of work. So proposed signature safe method was target and improved that recall and without losing accuracy, and for future we could try it on different data sets and try also implemented feature selecting approach to prevent let's say categorical features be more valuable for that system and hide non-useful features from original dataset. And yeah, also try it on real time, how it will works. Yeah, that's it. Thank you. Any questions?
Thank you, Bogdan. Okay, dear colleagues, any questions, please? No, so I have one. What is the computational complexity of your solution?
Yeah, good question for that. So unfortunately, I don't have such good results because we didn't have same hardware setup for baseline and for that signature safe method. So it's good to be done in in continuing of that research.
Okay, thank you. And colleagues, more questions? No, so thank you, Bogdan, for your report. Let's move on. And the next speaker, maybe Maria Nazarkevich. Somebody from...
Yeah. Hello, I'm Alexei Kuziv, sharing my screen.
Yeah, we'll present accelerated deep learning. Yes.
Yeah. Do you see my screen? Adaptive
Yes.
batch sizing, acceleration, multi-GPU training.
Okay, but can you switch into the presentation mode, please?
I am sharing.
Let me see into the slide mode. Presentation.
Okay. What do you mean by presentation mode? This one?
No. Now you have to press five
tab name slideshow in PowerPoint presentation.
Slideshow, and what's next? From
Firstly,
beginning,
enable editing. Enable editing. And after that, press F5 and share presentation.
F5, right?
Yeah.
I was doing that. Now you see?
Not yet.
Okay, let me reshare my screen. I will share another screen, entire screen. Do you see?
Yes, but
yeah, finally.
Yeah, I was doing that, but unfortunately, it doesn't work if I share only PowerPoint. Thank you. So yeah, I will present as an article about dynamic batch adaptation according to resources throughput. So thing is, once we train any AI model, whether it's LLM or other, we know that we have lots of steps, and thing is, we have to specify a batch. Yeah, we hardly can train all if we have lots of items to feed to our model. We should batch them, and thing is to how to do that. If we have fixed batch size, it's not the best way, because sometimes our if we have unlimited resources here, fixed batch size can work, and we can end up in great trained model. But unfortunately, we don't have unlimited batch size, and when Usually we pay for that because to have that computational resources at home, it's pretty much expensive pleasure. So that's why we order some hardware and train our model there. Thing is, even there, we hardly can fit to all the resources, and we hardly can get the best batch size, because since we pay for it, we want to our training process to finish as soon as possible. Thing is, we are trying to develop batch adaptation algorithm. So once we and it trying to change batch size according to resources consumed, and we see how that actually updates epoch training time. Usually, for example, in like image recognition, whatever, when you are training something, so epoch time is pretty much constant, like in YOLO or wherever. But here we actually updated batch size, and epoch training time per epoch reduces, and we see it's pretty much significant reduction. Thing is, we are calculating GPU consumption, CPU consumption, memory consumption. And if we see, for example, CPU and in GPU mainly, because GPU is main computation unit there, if we see that GPU is not used enough, we're increasing batch. If we see, okay, GPU is overloaded, memory consumption is increasing, we are decreasing batch. How are we doing this? We're having coefficients alpha and beta. So alpha is it's predefined constant at this stage of investigation. It's 1.5. We're increasing the amount of batches from initial to 1.5, and if it's still if next epoch is training time is worse than it was before, we're decreasing it but 0.8. Why? Just to like some adaptation of binary search. What is the best epoch size? And for example, if some cache is overloaded, yeah, because we have some data is stored in the cache, some data is stored into the random access memory and so forth. And it's possible even that's the best batch size which works on second epoch might not work on like 7 or 8 epoch as we see here. So then we decrease or increase batch size according to our computational rules. And thing is, it shows us really promising results. And if those coefficients alpha and beta, how we increase and decrease, can be calculated according to GPU or CPU consumption, that's our next step for improvement. That's pretty much it. Thank you for your attention.
Okay. Thank you for your presentation, dear colleagues. Any questions? What are metrics which are monitored to adapt the batch size?
GPU, CPU, and random access memory usage. Those are the most easy to get. Whether it's Linux container or or Windows, those metrics are the most easy to get, and they actually the main metrics which actually affects the computational speed. If GPU is overloaded, I mean, it would train much slower, right? Because not all the batches can fit the size. It tries to allocate additional memory from RAM, even from static memory, and static memory is slow, and that's why even though it's on the paper it should work faster, it actually works slower. That's why we are trying to adopt that batch size. It's not static. And the thing is, results are promising. That's why we decided to present.
I see. Thank you.
Thank you.
Colleagues, any more questions? No? Okay, Lucy, thank you for your presentation. Let's go to the next speaker. Petrovizhevsky, are you here? Are you ready?
Yes.
Yes, please. Up to 15 minutes, maybe 10, 15 minutes.
Can you see my screen?
Yes, we can.
Awesome. Hello. So my name is Petro Wyszewski, and I'm presenting work done together with Oleg Savenko, which is evolutionary learning framework for DLP policy adaptation in drifting environments. The problem is concept drift in data leak prevention systems. Let's say sales sends more emails before last quarter of the year, and DLP system is configured for normal situation here. And we end up missing a lot of, we end up producing a lot of false alarms. If we tune for today, we can miss something that happens tomorrow. If we are too permissive, we're missing leaks, too strict with our DLP configuration. There is a huge burden on analysts who actually analyze the alarms, whether they're false or not false. So retraining always is not a feasible option, is not always feasible options, because retraining means downtime. Retraining requires labeled data, which might be not available or available later. So the idea is, and current approaches like error tracking, it essentially monitors error rates. It triggers whenever errors exceed threshold. Distribution shift is again detecting using tests on Windows. And multi-model ensembles are just running multiple models, which is working really great, but it is resource intensive, and both previous methods are essentially reactive methods and require labels. And so our approach is to kind of combine evolutionary algorithms and unsupervised training to just detect drift and then tune the rules in place to kind of match the changed environment. And the solution essentially is a multi-objective optimization, where the main 5 objectives are missed leak, leak risk, false positive load, latency, complexity of the rules that are enforced, and alert stability. Operational constraints are P95 less than 100 milliseconds, memory shouldn't be exceeding 512 megabytes for computing budget, and yes, so the overall system is we are receiving events, feeding to the drift detector, selecting crossover mutation for adapting our genome, which essentially just decides whether this event should trigger alarm or it shouldn't. To mitigate kind of overtraining, the evaluation is done with exponential forgetting, and also to avoid kind of spikes, throwing off, or sudden system degradations. There is an archive of policies that are compared with current one, and if current one is significantly worse than one of archived ones, we just use the old one policy just to avoid kind of going into frenzy. So mutation intensity essentially tracks environment stability, and it works in a way when there is drift, the policies are mutated actively, and when there is no drift detected, mutation is really low, just to preserve working policies. And we are monitoring model uncertainty entropy. Therefore, we don't require labels. We just look, and also we are mixturing weights, like between, we are mixturing multiple policies, multiple rule sets, just to kind of smooth over the transition. Yeah, so the main benefit is for the actual policy changes, for changing the weight of policy of rules in a policy, we don't need human supervision. Experimental results didn't show the best cost. It means that sometimes we missed some alerts, but the main goal was to decrease load on analysts and to reduce alert variation and reduce false alarms. By smoothing out, by producing more stable load of alarms, we kind of allow for better, more predictable workload. And this is a trade-off because we will be missing a couple of actual alarms due to that. But given that the main goal and the main aim for this algorithm is to use for corporate DLP systems, workload of analysts is kind of main goal here and fitting into the computational restraints. Across board, mainly numbers are pretty similar. Baseline methods were different, but more or less cost was within either same or a bit or 2% worse, but alert volatility decreased by approximately 50% across the board, sometimes a bit higher, sometimes a bit lower, and service level objectives were met. And obviously false alarms per events were decreased. That's how the volatility was reduced, because we smoothed out the spikes in false alarms when there's sudden drift occurs. For the experimental tests, drift datasets were chosen, while there are different datasets available in it. There is abrupt drift, there's gradual, mixed, and some real data like electricity, weather, just for testing various kinds of drifts. Yes, so by drift type, the information is kind of pretty much similar. So yeah, lower false alarm rate, volatility reduction. It's a bit bigger, a bit smaller, depending on the data set, but within same, let's say, margins. And yeah, so what was achieved? Evolutionary approach essentially balances a couple of objectives. We are still catching alarms. We are trading off a bit of missed true alarms for less false alarms, and therefore decreasing the fatigue of security analysts. And for actual practical deployment, this is planned to be expanded in a more complete system for data leak protection that focuses mainly on profiling users and actors in corporate networks. Also for labeling data like emails and network packages being transmitted inside corporate networks. For actual implementation, there is a lot of kind of nuances to it. Obviously, there is a problem of cold start that needs to be addressed, and for cold start, it's better to have some kind of labeled data to train the model on and tune the parameters. Otherwise, without a cold start, might take a bit of a time to actually start performing well. And the actual rollout of new policies should be like behind some canary mechanisms. If something goes wrong, just roll back to the old policy, and new policies should be rolled out gradually across the corporate network. And overall, the parameters of drift detector requires tuning, and obviously initial labeled data will be immensely helpful. Also, having, if labeled data is available, some sporadic tuning mid-time, let's say, work of this algorithm will also improve accuracy. So thank you for your attention. If you have questions, please do ask.
Okay, thank you for your presentation, dear colleagues. Any questions, please? No? I have a question. How are false positives, false negatives, and maybe operational cost balanced in fitness simulation in your solution?
So we are optimizing for false positive loads. So false positives are like one of the main goals to decrease, and latency and complexity. Latency essentially comes from the complexity. The bigger the rule set, the worse, the harder it is computationally, and the worse it's for analysts to work with. I mean, obviously, there is a lot of really awesome black box systems that are more accurate, but they produce essentially, they are black boxes. Therefore, it's hard to kind of predict the latency they will produce, and the rule set will be not available for actual analysts to check and verify the logic behind the false or not false alarm. But the optimization function is comprised of false positive load and complexity of the functions that will actually influence latency as well.
Okay, thank you, Petro. Colleagues, no question? No. So thank you for your presentation. And next speaker is Igor Holovko. Are you ready? Please share your screen.
Hello, do you hear me?
Yes, we do.
Okay, great. Let me share my screen. Do you see my screen?
Yes, but please switch on to presentation mode, please.
This is PDF format.
I see. Okay.
Yes. So hello, everyone. My name is Igor Golovko, and I want to share my work in using AI stacking ensemble to obfuscate .NET code. So first of all, we need to define our motivation, problem definition, and purpose. So what is motivation? .NET platform and C#, for example, it's a high-level programming language that during compilation time will compile in intermediate language. So it's not fully a machine language. And this is a good thing for like it has pros and cons. So pros that's we can use a different languages, for example, F#, R# from .NET, and we can combine different language, and as an output we will have intermediate language that will work. But the problem is it is easy to decompile, and it is easy to predict and analyze proprietary algorithm and some programming logic. So we have a static obfuscation tools, but the problem with the static obfuscation tools that they are predictable. So if we have some the same intermediate language sequence, the output will be almost the same when we use a static obfuscation tool. So and that's why we need to invent something new that will hard to for our reverse engineering tools to decompile our ill code, and that's where actually our AI models could help us. So the problem definition, that's .NET program is represented as intermediate language code. Intermediate language ill code is a high-level byte code that closely reflects the original source code structure, which make it easy to decompile and analyze using modern tools. As a result, attackers can recover program logic, proprietary algorithm, or security critical mechanism. So also can be security vulnerability. And the now the purpose, what the purpose of this work? To transform ill code into a new version that can behave exactly as the same code during execution, but it should have much harder to understand, analyze, and reconstruct from ill code. Okay. I achieve this thing using a stacking base assemble. So a high-level overview of this stacking base assemble is that at the first level we have 3 deep learning models operating in parallel, and each model focusing on specific property of ill code. For example, on short-term memory, this is a sequential analysis. LSTM model analyzes ill code as a sequential sequence of instructions. It learns execution patterns, control flow regularities, and repetitive instruction sequence. Role of this model in obfuscation is identifies predictable execution paths, detects linear or loop-based patterns, highlight code regions vulnerable to a simple decompilation. Another model that I use in stacking base assemble, it's autoencoder, deep autoencoder. So it's analyzed in another way. It's analyze semantic representations. The autoencoder learns a compressed latent representation of ill code that preserves semantic meaning while removing synthetic details. Role of obfuscation in obfuscation encodes functional behavior into latent space, enables generation of structural difference but equivalent code, helps preserve semantic during transformation. And the last model, but not least, it's a transformer. So a transformer analyze global context modeling, so it can analyze, it can find a deep, like a global dependency between different ill code regions. So the transformer captures large dependencies and global relationships between ill instruction using attention mechanism. And role in obfuscation, it understands the iterations across distant code blocks, models complex control flow, with which allows us actually create more complex complexity and calls the relationship, and supports context-aware obfuscation decisions. And we have on level 2, on the second level, we have our meta model. This meta model was actually is built based on a multi-layer percentron, and second level consists of stacking meta model implemented as a lightweight multi-layer percentron. This model receives feature vectors from all basic model and learn how to combine their insights. So responsibility of the meta model is to evaluate multiple obfuscation strategies, select transformation type and intensity, balance protection strengths, and performance overhead. The meta model is trained using integrated quality metrics, ensuring that a decision to improve resistance and to reverse engineering without breaking program behavior. Formulation of the problem. So let .NET assembly A compile it to intermediate language with a set of methods M. Intermediate language represents a set of instructions. So we have I1, I2, and so on, IN, with a control flow graph where the vertices of V are the basic code. So graph is V, it's a basic code blocks, and E, it's edges that represent the transformation between them. The process of obfuscation consists of purposely changing the structure in such way that the functional behavior remains unchanged, but the code becomes difficult to analyze. That means that obfuscation is an operator that transforms input IL code into a new version of it that represents the execution semantic, that preserve execution semantic, but has a significant different structure. So we can see that IL with dash is obfuscated, parameterized by a vector theta that defines the type and depth of transformation. And the attacker model. Attacker model is this reverse engineering tool with a binary access in the compilers. Goal is near source reconstruction and logic extraction. The main goal of obfuscation is maximize resilience, code complexity. This is based on cyclomatic complexity stills, while minimizing overhead, runtime, memory, and size. Summarized by integral Q-metric characteristics that preserve IL validity, verify it, and just-in-time compiler, JIT compile compatibility, deterministic build integration, and suit test. So we see our integral Q-metric. It's a sum like sum with resilience, stills, code complexity, and minus overhead. Weighting factors were selected manually. So in this specific experiment, value factor, the most important at this experiment was resilience. So as you can see, it has the higher weight. Okay, so let's move next and formalize the stacking assemble. So the results of basic model are represented in the form of feature vectors, H1, H3. So it's we have like LSTM, deep autoencoder, and transformer, which are passed to the meta model, which performs generalization and makes a decision on the optimal type, depth, and intensity of obfuscation transformations. Yeah, so we can see from this formula, TI corresponds to a separate model, and the meta level T meta summarize the results to form the final obfuscated IL code. Thus, stacking implements the principle of integrating the knowledge of different models into a single system that adapts the complex of the application. And each stage has its own functional role: structural analyzing, representation formation, result integration, and obfuscation code generation. Data transfer between modules is carried out in a vector format, which allow us to minimize information lost and allows for a quick model updates without changing the system architecture. Okay, so the next slide, we can see architecture of stacking obfuscator. So we have .NET assembly. It could be like dynamically linked library or execution file, transformed into IL code. Then we have IL parsers that will tokenize for us IL code sequence and extract the control flow graph to understand execution of this application, of this program. Then we try to extract the feature. So we create token embedding, static feature, and profiling metrics. And then we set this feature to our 3 models. And each models analyze this feature, but based on their own requirements. So sequence analysis, for example, for LSTM model, autoencoder semantic compression, latent code representation, transformer, it's a global context modeling, and attention-based relations. After that, we send our output, our results from our base models to our meta model aggregated, and based on results from basic models, meta model aggregated show us a decision, so which obfuscation strategy we can use in this specific case. And then we have a map decision that will actually provide us certain obfuscation strategy, and IL writer will apply this transformation according to our strategy. And the final stages, it's like verification, unit testing to see whether program functionality, program behavior is preserved. So we have the same results before obfuscation and after obfuscation. And also we can integrate our system, for example, to CI/CD pipelines, and as a result of obfuscated program, it will be CI/CD artifact. Training flow methodology. So let each program PI is first transformed into the IL level of feature representation. 3 heterogeneous base model independently extract complementary latent feature, sequential execution pattern, semantic representation, and global context dependency, as shown in group 1. So we can see these features, H1, H2, H3. After independent training, the base model are frozen and their outputs are concatenated into a stacked feature vector. This is group 2, preventing feature drift during the meta learning. And meta model implemented as a multi-layer percentile maps the stacked representation to a decision vector that encodes obfuscation operation probabilities. The meta model is optimized with respect to composite quality metric, balancing resilience, complexities, stills, and overhead, as defined in group 3. This two-stage training strategy enables adaptive obfuscation while representing semantic correctness and execution stability. Now, after learn stage, we can actually be ready to do our experiment. So we prepare data preparation. So we set 120 assemblies, .NET application in various size and nature, utilities, libraries, server modules, project with a saved set of unit tests. So it is very important to have for each of these assembly unit tests that can tell us do we preserve functional behavior of the application or not. Partitioning, then we do partitioning, so 80 assemblies for training selection and hyperparameters of models, and 40 assemblies for a test sets evaluation. For like a proof of concept, syntactically generated IL variants are used, and as the diversity of structure, a loop condition asynchronous call is controlled. Preprocessing, extraction of IL tokens, construction of CFG, generation of feature, token embedding. That's what we discussed during learning methodology. Yeah. And basic models are trained independently on the same tokenized example, and for autoencoder, the recognition loss is used. LSTM model is trained on a classification task and internal IL templates. Transformer concentrate on context, recovery, masking task, masked token prediction. And after training each basic model, the obtained feature for the training and validation sets are stored. And meta model is trained on the combined vectors with the goal, the vectors of obfuscation operation, to maximize our integral matrix Q. So the meta model loss function combines the semantic recovery error from test and the structural difference indicator and overhead control. After training, the entire assembly run on the test set to generate obfuscated assemblies. And results of experiment, we can see, for example, we have our 5 metric. It's resilience, stills, complexity, cyclomatic complexity, and overhead, and our integral metric. So I compared with the 3 famous obfuscator tools. It's Confuse X, Babel, and Smart Assembly. And as we can see, resilience, we have a good results for resilience metric. This is like the most increased value compared with other metrics. But we can see that overhead we have more like resource utilization during our AI obfuscation process. This is like a trade-off between our AI obfuscation, our security IL code, and yeah, performance, let's say. And conclusions. This work introduces stacking-based assemble approach for automated obfuscation of .NET intermediate language code. Unlike traditional rule-based obfuscators, the proposed method leverages deep learning models with complementary capabilities: LSTM for sequential execution pattern, autoencoder for latent representation, and transformer for global contextual dependencies. And meta model integrates these 3 heterogeneous representation and adaptively select obfuscation strategies, enabling context-aware and non-deterministic transformation. The 2-stage trading process with a frozen base model ensures that stable feature extraction and prevents semantic drift during optimization. Experimental evaluation demonstrates that the proposed approach increases resistance to decompilation, improve structural diversity of IL code, maintaining semantic equivalence with acceptable overhead. Yeah, so the result confirms that the assemble learning outperforms a single model, and static obfuscation technique is in terms of robustness and adaptability.
Anyhow,
That's
thank you
it.
for your presentation,
you
colleagues.
for your
Any
attention.
questions, please? Because we have not the time, just one short question. And how does obfuscation affect just-in-time compilation and execution performance?
Yeah, so execution performance, we also will have some decreasing in execution performance, because it is quite possible that we will have it's like one of the obfuscation strategies, it's a control graph obfuscation. So we can have some like unnecessary, for example, very road roof explanation. We have like a loop that actually this loop is redundant. We do not need to do this loop to get results from some specific method. But this, when we decompile the code, we will see this loop. That loop can, what it does, it's just increase cyclomatic complexity for our IL code. Yes, it will decrease performance, but again, we need to understand overhead trade-off between slow down the performance and secure our proprietary algorithm, and yeah, that's
okay. Thank you for your answer. Thank you for your report. Let's move on to the next presenter. Okay, Andrei Reho, are you here? Are you ready?
Yes, I'm ready. Good afternoon, colleagues.
Yes, please.
Good afternoon.
Харченко, Рехов, Кондратюк. Artificial intelligence.
I do not see your presentation. Excuse me. Please share your screen, please.
Харченко, Рехов, Кондратюк. Artificial intelligence based protection of unmanned aerial vehicles, communication channels against adaptive artificial intelligence jamming based on pure learning. The aim of this report is to create model of communication channel, ground control station, unmanned aerial vehicle attacker. Implement the following scenario: attacking artificial intelligence, studies the drone's channel switching history, and jams the most likely channel. Defensive artificial intelligence uses Q-learning to deceive the attacker by avoiding predictable patterns. This is our model, which consists of ground-based station, unmanned aerial vehicle with AI-based protection, and attacker with adaptive AI jamming. Relevance of the topic. Modern unmanned aerial vehicles are critical systems in military rescue and commercial operations. Their operation depends on the reliability of the command and control channel and telemetry. However, in electronic warfare, the radio channel becomes a primary target. This table demonstrates limitations of classical protection methods. Fixed frequency, easily jammed, false random switching, predictable when analyzing history, wideband signal, requires high power, vulnerable to narrow band jamming, manual frequency control, slow, doesn't scale. Model description. Proposed reinforced learning-based AI defense model enables adaptation to unknown attacker strategies without prior training, minimization of predictability through a balance between exploration and exploitation, operation in real time on onboard systems with limited resources, scalability to a swarm of drones with coordinated defense. Why we use Cure learning? Environment model. In Cure learning, not needed. Discrete action. 8 channels are ideal. Online training. Cure learning, yes, step by step. And resources, 520 bytes of RAM. Scenario. Attacking AI optimizes jamming frequency by analyzing the drone's channel history. Defensive AI uses reinforcement learning, specifically Cure learning, to dynamically select a secure channel. Goal is to maximize the time to successful transmission while minimizing energy and computational costs. Practical significance. Adapt to unknown attacker strategies without pre-training. Minimize predictability by balancing exploration and exploitation. Operate in real time on resource-constrained onboard systems. Scaling to drone swarm with coordinated defense. Mathematical model. Defender AI on unmanned aerial vehicle uses Cure learning to select next channel. Drone's goal is to maximize its cumulative reward, successful transmission. Attacker's goal is to minimize drone's reward. Agent selects actions based on data from Q-table, which is matrix whose rows represent possible states and whose columns represent agent's possible actions in these states. Values in Q-table reflect expected total reward for performing the action in a given state and subsequently following the optimal policy. After each step of the agent, Q values are updated using Bellman equation. Agent selects actions based on values in Q-table using epsilon greedy strategy that balances exploration of new actions and exploitation of known actions with the highest Q values. Bellman equation for Q values. Here, Q as A is expected Q value of A state and action. R is immediate reward received after performing action A from state S. Gamma is discount factor representing the importance of future rewards, usually value between 0 and 1. Max is everything after it is maximum Q value for all possible actions A from next state S. Bellman equation allows agent to evaluate long-term consequences of its action, taking into account current reward and expected future rewards. Attacking AI calculates transition metrics. Sliding window uses 50-step window. Frequency-based jammer jams the most frequent channels. Results. Final cumulative reward 72.5 indicate feasibility of practical implementation of the system on board unmanned aerial vehicle. Compact Q-table 8 on 8, 64 cells and low power consumption, less than 5 millivolts per switch, make the solution feasible on unmanned aerial vehicle systems. This is dependence of cumulative reward on episodes of training. We can see that maximum value is more than 70. Forward error correction is error correction method that adds redundant bits to data before transmission, allowing the receiver to independently correct errors without repeating the request, so-called ARQ. In the context of our tabular Q learning simulation against reactive jamming, forward error correction is critical. It compensates residual bit error rate caused by jamming and reduces packet loss rate. Without for error correction, even low bit error rate results in high loss for large packets, which is unacceptable for real-time unmanned aerial vehicle communications, such as video and telemetry. Here we can see dependencies of packet loss rate on packet size with and without forward error correction. Red line is no forward error correction, and when t parameter t is 10, this is the lowest dashed line. Forward error correction is very effective. Conclusions. Q-learning-based unmanned aerial vehicle protection system, robust against adaptive jamming, has been developed and tested. System is deployable on board, energy efficient, and scalable. Developed Q-learning-based system demonstrates high effectiveness in protecting unmanned aerial vehicle communication channels from adaptive jamming. Despite limitations associated with the simplified results, confirm the potential of reinforcement learning for solving electronic warfare problem. Thank you for attention.
Thank you, Andrei, for your presentation. Dear colleagues, any questions? Okay, I have one. Andrei, what are the main limitations of your solution?
What do you mean limitations? Our purpose was to create and to test the simplest on-board anti-jamming system. It was our first step. Now we continue. So these results didn't satisfy us, and we continue. Now we created system based on neural networks. So it was the first. This investigation. It is the first step. We have seen that it is possible to create on-board anti-jamming system. Why? Because cumulative reward is increasing. It's working, and it's beginning. I can say so.
Okay. Thank you. Thank you for your presentation. And the last but not the least presenter is Igor Prokofiev. Are you ready?
Yeah, thank you, Sergey.
Please.
I will try to speak very fast and make my presentation very fast. Do you see my screen, Sergey?
Not yet. Oh, you will share? Yeah. Now we see. Okay. Yes,
okay,
please.
Very good. So the name of my study is an integrity model for microservice system based on the code equality matrix. So the motivation is pretty simple, that modern enterprise system increasingly rely on microservice architecture, and nowadays it's very popular. And however, it is really hard to identify the code equality of such systems, because microservice architecture contains of sometimes of 10 and dozens, or sometimes of hundreds small services. And for development teams, it's much more important not only to know what exactly code equality of the specific microservice, but the overall microservice index. I'm sorry, the overall quality index. So, and also the architecture quality is not static. It evolves continuously and may silently deteriorate over time. So, an organization urgently need a measurable and objective way to assess the health of microservice architecture and detect problems early before they lead to failures or costly to refactoring. So, and problem of statement. So the existing quality assessment solution primarily evaluate internal quality metrics at the level of individual services or components. So it's like the basic quality metric we know is basically most of code attributes quality metrics are based on the lines of code and cyclomatic complexity, and let's say they are like inherited from this. And but the problem is that such metrics, they never give developers and engineers the real quality of the complex service-oriented or microservice architecture. So that's the problem. And here is the next slide about the limitation of classical metrics. So the traditional software quality metrics, such as line of code, weight methods, reference per class, and other, they design it primarily for monolithic or object-oriented systems. And they successfully detect structural complexity, code smells, and maintainability challenges, but they fundamentally do not capture distributed runtime behavior, ignore inter-service dependencies, and overlook architecture smells such as shared database or distributed monoliths. This is well-known anti-patterns. So thus, they measure code quality, not the architectural integrity. And the research objective of this study is, the goal of this work is to develop a quantitative architectural integrity index for microservice systems that integrates internal software quality, measures the stability of inter-service communication, reflects how architecture evolved over time, enables continuous monitoring rather than one-time evaluation, and can be automatically computed using existing development of and observability tools. So, and proposed solution is based on three different, let's say, models. So it's like a conjunction of internal and external, and evolution, or evolution can be named of dynamic models. So internal, this is how each microservice is built and what its, let's say, generic overall quality. External, it's about the how each microservice depends on another microservice, and this is the goal of this stage. On this stage, it is important to identify what microservices, let's say, are more important, what are less important, and to make something like a importance index. And evolution or dynamic vector or overview is about the code is not static, it is changing during new commits, and it must be possible to identify new issues and what's going on with the code quality in time, so to make some prediction. So for each service, what we collect internal code metrics like complexity, coupling, size, duplication. This is like works for any monolith software. Then architectural indicators like resiliency, contracts, dependency level. So this is about if the microservice architecture is built in the right way. And dynamic evaluation metrics is a code churn drift releases. So it's about how often the code is changed, and do we have a code degradation on specific level or not. And to compute the architectural integrity index, I employ the explainable Boosting matching, a modern interpretable machine learning technique. And key advantages are full transparency of precision, ability to enforce monolithic trends, resistance to noise and overfitting, and generation of human-readable explanation. And so the first layer is an internal integrity layer. It is based on well-known code quality attributes like cyclomatic complexity, weighted methods per class, response for class, service size, it's lines of code, and code duplication ratio. And all metrics, it must be normalized from 0 to 1. It's like a very basic job for any mathematic. And the next layer is external and architectural layer. It can be named external or architectural. I think this is a better name. And even perfect internal code cannot guarantee architectural quality if services interact purely. It means that no matter how cool you build, or how if you have a very great code quality on specific service, but if such services, they are connected not in right way, or it is not possible to make like predictability, and they do not use the modern, they're not without the resiliency, or for instance, they use a shared database and or any other anti-patterns related to the microservice architecture. It means that the overall the quality of such system will be like bad. So and the next layer is a evolution and learning layer. It's about how we see the system in a time, so during the next commit. So architecture quality is moving a target. The layer analyzes how the system evolves and whether changes remain controlled. We measure commit and modification activity, code churn level, drift in complexity metrics, frequency and rhythm of releases, evolution of dependencies, and so it needs to say that healthy architecture will predictability and sustainability. Degraded architecture accumulate instability gradually. This layer detects such risk early. So for the data sources, the model relies entirely on the modern engineering organization already collects like a static analysis tools like SonarQube, and it is another version of a Sonar Cloud, which can be used like a SaaS. Version control systems like a JIT, observability platform Prometheus, Jagger Open Telemetry, IP specification, contracts, message brokers, analytics, CI/CD deployment pipelines, experiment and results. So in order to make so how the experiment was built, I prepared the software built on .NET and C#. This software, it could analyze a specific folder of .NET application. It could identify a list of if this is like the monolith or microservice architecture, and on each level it is trying to identify number of code quality attributes and also dependencies between them. Dependencies are based on the OpenAPI file, so it's like about the Swagger to we ensure that the systems can interact with each other, and also it scans to identify if there is some resiliency, like retry policies and other, let's say, modern practice in microservice architecture to identify if the system design is correct. So, and the experiment was built on a real software I built in past, and my goal was to try to play around with very pure software code quality, which was, for instance, the software written a long time ago, and with more modern. And so in practical value of such study is that the proposed model is not purely theoretical. It has a direct industrial applicability. It enables continuous architecture monitoring, early detection of degradation and risk, evidence-based refactoring planning, reduction of long-term technical debt, increased reliability and resiliency. Conclusion and impact. So it is possible to use such this system I built to connect it to the CI/CD and improve, in fact, the development process related to the C++, to the project written on C++ or inherited languages. And the future work is to improve the so the future research directions of automatic learning of matrix weights. This is very important here, and forecasting architectural degradation, integrating semantic analysis, and anomaly detection based on the behavior patterns. Thank you for your attention. I'm done.
Thank you, Ivo. Thank you for your presentation. Dear colleagues, any questions, please? One, okay, I have one. So how does your model scale with increasing of microservices?
You mean if my model supports the scalability?
Yes.
Well, on this stage, let's say by default, my model could detect large microservice architecture, but up I think to something like 100. But to be honest, I did not play with very large microservice architecture because nowadays it's really hard to find such models. But you raised a very good question, and I will think about it because this is another good point where I can improve such system to ensure that it could like handle hundreds of microservices.
Okay, thank you, colleagues. No questions. Okay, dear participants, I'm happy to conclude that our session is ending. So thank you for your reports, for your questions. See you. Bye-bye.
Thank you. Have a nice day. Bye.
Bye.
Thank you. Bye bye.